Hi guys, well, another chemical engineering tutorial brought to you by the ChemEng student. In this lesson we're going to take a look at fluid dynamic viscosity models. Now we already have a full in-depth tutorial on shear thinning fluids using the power law model, which I'll put a link in the description to that video. So here what we're going to look at is we're going to talk about the viscosity in terms of real fluids. Now we could have a plot between the shear stress and the shear rate, and this graph, which you should be familiar with, is called a rheogram, and it gives us an indication of the fluid behaviour. So say we had a fluid of unknown characteristics, then what we could do is we could measure subsequent shear stresses against shear rates. We could plot them on an XY axis and that would produce a rheogram, and from that we could deduce what is the behaviour of our fluid. Now essentially there are two types of fluids defined by this relationship. The first one being a Newtonian fluid, whereby the viscosity, it changes at a constant rate. So as the shear rate increases, the shear stress increases, and the relationship here is linear, so that we can predict what the viscosity is, or say we know the viscosity and the shear rate but we want to know the shear stress, then we can predict using a linear model. Now what that also means is that the viscosity given by mu is constant. So that means that it does not change regardless of how much shear rate we put on and how much shear stress we expose the fluid to. The viscosity will not change. Whereas if we look at non-linear relationships, then this is just one of a couple of different types, but we'll look at what this one actually is in just a second. But this one is called a non-Newtonian fluid. So non-Newtonian will have its viscosity change in either a positive or a negative way with an increasing shear rate and shear stress. So essentially what we can say here is that we have two different behaviours. We have non-Newtonian fluid flow, which means that the effective viscosity will change with respect to the shear rate, whereas Newtonian, the effective viscosity will remain constant regardless. Now one way that we can prove this is that the viscosity, so if we were to work out what the viscosity actually is, then the formula for viscosity in terms of the shear stress and shear rate is we have the shear stress, which is given by tau. So normally it's tau yx or xy. So it would be delta tau, which is the change in the shear stress, divided by the change in the shear rate, which we normally denote by the Greek letter phi. So this change is actually a gradient formula, and this would be evident because we have dy, so the change in the y divided by the change in the x. So our viscosity model, or the viscosity, is actually a measurement of the gradient between these two parameters. So we can actually look at this graph and deduce what type of fluid we actually have, because say from this point to that point we have a specific gradient, so it's quite steep. Whereas if we come up here, then the gradient is much less. So that indicates that we actually have a shear thinning fluid, because the viscosity is getting less and less as the shear rate increases. Whereas if the graph went in the other direction, i.e. we had something that looked like that, then this would be a shear thickening fluid, because the viscosity is starting to get higher. The gradient between the shear rate and shear stress is increasing. So that's the theory, the background as to how viscosity actually works. Now when we have significant deviations from the power law, which is what we've seen in the video that I'll attach in the comments, then this tends to happen at either low or high shear rates, because the power law model will only be considered for a certain range of values. Now a model that will take into account the zero viscosity and the infinity viscosity. So the power law doesn't actually account for these terms. So these are the extreme values, i.e. the very initial viscosity and the infinite viscosity. Now, the Carro viscosity model is just one which is based on the molecular network. And this considers the limitations in terms of the viscosities of the initial, so the zero viscosity, and the infinite viscosity. So the Carro model is one of the first ones that we would consider on an chemical engineering program. Now it's expressed as follows. So we have our viscosity at any given point in the system minus the infinite viscosity divided by the zero viscosity minus the infinite viscosity. And that is equal to, now this is the curve that we could actually plot this. So this is what, we had the power law model. So this is the way in which we can actually plot what this looks like. So what we have here is we have 1 plus lambda multiplied by the shear rate to the power 2, all to the power of n minus 1 over 2. Now n and lambda are curve-fitting parameters, and as such we can either deduce them through experimentation or we can get them from published literature. Now we have an extensive range of chemical engineering and engineering reference texts on our website, which I'll put a link in the description to that, and you can browse through a wide range of texts, reference books and solution manuals that will help in retrieving these key pieces of information if you need them. Now the Carro viscosity model describes shear thinning behaviour, and this does it over a wide range of shear rates, but only at the expense of the added complexity of now having 4 parameters. Because this model predicts that for Newtonian fluid behaviour, that the viscosity will be equal to the zero viscosity, i.e. the viscosity doesn't change. Because the initial viscosity, if it was Newtonian, would be exactly the same. The viscosity wouldn't change. But if this was for non-Newtonian, then this would not apply, because the viscosity will change as the shear rate changes. Now, neither n would equal 1 or lambda would equal 0 or both. So that means that if we were to have Newtonian behaviour, we would either have an n value of 1 or a lambda value of 0. But there is nothing to say that we couldn't have both. Now this model was designed back in the 1965, the cross model, because the cross viscosity model, while it does have a 4-parameter model, it is simplified ever so slightly, because we still contain the same left-hand side of the equation. We still have the difference between the viscosities between the initial, our actual viscosity at that moment in time, and the infinite. But this time we have 1 over 1 plus some constant k multiplied by the shear rate to the power n. Now n in this case for shear thinning fluids must be less than 1. And k is also another curve fitting parameter. Now the limitations here is the mu naught and the mu infinity, because these are the limiting values of the apparent viscosity at low and high shear rates. So this model reduces to Newtonian fluid behaviour as k tends towards 0. Because let's think about it, if k tends towards 0, then this entire term would become 0. So the ratio between these would be 1, because we'd have a 1 to 1. So that would indicate that these values are exactly the same, because these would of course cancel each other out. If this was 1, then in order for this to, for this equation to satisfy, i.e. if we had this scenario, then in order for this to satisfy, we must assume that mu equals mu naught, i.e. Newtonian fluid behaviour. Now, we do have other sets of conditions in order for this to work, in that, if we go for extreme values, so that our mu is considerably less than mu naught, or mu is considerably greater than u infinity, then it would reduce to the familiar power law model. So either or of these conditions are met, then the model that we would use, rather than using the cross model, which encompasses 4 parameters, we could just use the power law model. Now, the Ellis model is when the power law deviations are only significant at low shear rates, then it's more appropriate to use the Ellis model. And the Ellis model looks something like this. So we have our viscosity that we want, and then we have the viscosity at a zero shear shear viscosity, and the remaining 2 constants, which is alpha and tau half. Now, the alpha is again a curve fitting parameter, but tau a half is in respect to the shear stress this time, because the index alpha is essentially a measure of the degree of the shear thinning behaviour, i.e. the greater the value of alpha, the greater the extent of the shear thinning behaviour is actually going to be. Now, tau a half represents the value of the shear stress at which the apparent viscosity has dropped to half its shear value. So that means that this value here is half of what the apparent viscosity shear stress actually was. So when we know what the apparent viscosity is with its respective shear stress, if we halve the shear stress, that would give us tau a half. Now, this model predicts Newtonian fluid behaviour in the limit between tau a half tends towards infinity. Which makes sense, because if the half gets closer and closer to infinity, then we don't start to exhibit the non-Newtonian behaviour, because this would tend towards being a value of 1. Now let's take a look at a working example here. So it tells us that the viscosity of a fluid decreases to half its zero shear rate viscosity at a shear stress, so we have a shear stress of 6.8 kilopascals. Now the fluid flows in the Ellis model, so we're now told which model to use. So we need to use the Ellis model. That's the one that we just seen, so that's this model here. Now we have a degree of shear thinning behaviour to be 2.1, so that's our alpha value. Now the fluid exhibits a viscosity of 850 Pascal seconds, and this is under a shear stress of 4.1 kilopascals. We need to calculate the viscosity of the fluid at the zero shear rate, i.e. mu naught in Pascal seconds. So what we're essentially doing here is we're just working backwards, because we know what the viscosity is initially. The viscosity is for it's 850 Pascal seconds under a 4.1 kilopascal shear stress. So what we can do here is tabulate the information that we are given. So we know that we were told that the half occurs at 6.8 kilopascals. So tau a half, or half the shear stress, is 6.8. We were told alpha is 2.1, and we know that for a shear stress of 4.1 kilopascals corresponds to a viscosity of 850 Pascal seconds. So that means that we know that mu that corresponds to a shear stress value of 4.1, we know this value, we know that, we know this, and we also know alpha. So the only unknown here is mu naught. So we can substitute in our values. We take the ratio of 4.1 over 6.8. We'll take that to the power of 2.1 minus 1. So we get to the power 1.1. We'll then add that to 1. We would then bring that across and multiply it by the 850. So you would pop that into the calculator, and that would tell us that the viscosity at zero shear rate is 1337.2 Pascal seconds. And again, you can just always include the units if you were ever unsure, and just ensure that you get it to the correct units. But that's how you would go about solving questions like that. So that's the end of this lesson. Thanks for watching. Hopefully this was helpful in understanding the concept and idea of viscosity and how we can, express it in terms of the graphs, plotting against the shear stress, the shear rate, how we can deduce what the behaviour is, and getting familiar with some of the models. So if you like this video, please like and subscribe to the channel. It really helps us reach as many chemical engineering students as possible. Thank you for your time, and we hope to see you in another video.